as an example of a singular matrix, that is to say, remember, a matrix with no inverse, we could let A be the 2 by 2 matrix that's 1 in the upper left corner and 0 everywhere else. I claim that there's no inverse matrix A such that A times A inverse equals the identity matrix. To see that, let's multiply A by an arbitrary 2 by 2 matrix and see what happens. Now, what happens, as it happens, is that the second row of this matrix gets turned to 0. And remember that I, the identity matrix, has 1s down the diagonal and is 0 everywhere else. Well, we could make this 1 and we could make this 0, but we're never going to have a 1 down here in the lower right. So this product can never be the identity. As a matrix that is non-singular, that is to say, it has an inverse. Well, like I said, almost anything would do. For example, the 2 by 2 matrix, 1, 2, 3, 4, is non-singular. We are not yet in a position to find the inverse. But if I tell you that it's -2, 1, 3/2, -1/2, then you can verify that this is the inverse of this via multiplication. 1, 2, 3, 4, -2, 1, 3/2, 1/2. Let's see. -2 and 3 give 1, 1, and drop the negative sign. 1 and -1 are 0. -6 and 12/2, that's +6, That's 0, 3, and -2 is 1. And if you swap these matrices and multiply in the reverse order, you will again get the identity matrix.